What a pleasure to be with you this morning and have this opportunity to talk to you about materials for tomorrow, really something about the transformative power of chemistry. And I'm going to pick on one particular material, one that maybe some of you are familiar with. I'm going to talk about blood collection tubes. That first sounds like it doesn't, not very exciting. How many people have ever had their blood taken? Huge numbers. I tell you, in the United States, I only have the figures for the United States, 3 billion tubes are made a year in which we collect blood and analyze it. It's one of the major ways of doing things. What happened is a story. This man, Dr. Rafik Bowen, is head of the Stanford Hospital in charge of drawing and analyzing blood. He came to me and he said, I got a problem. Help, can you do something? And I was surprised. I really remembered some chemistry from long ago and was able to convince, at that time, a graduate student of mine, Samuel Kim, to give it a try. And very quickly, something worked. And I'm going to tell you about how to change the surface of blood collection tubes that are plastic from hating water to loving water, to becoming hydrophobic. And I'll go through the reasons why. Let's begin with the importance of this topic. Turns out blood collection and processing are the two major pre-analytical steps in clinical laboratory testing. And if you look into where the errors occur, often in that phase. It's important. Okay? And I thought I'd now go through the history of blood collection tubes. What is it like? What has happened? People started using reusable glass syringes with steel hypodermic needles. Okay? Those were the first devices. And the glass syringes were expensive to manufacture, and they could easily break. What ultimately prompted their replacement, however, was not that fact, but rather something which I think will be obvious to everybody. Okay? You don't want to keep using the same needle in people. And this led very much to outbreaks of hepatitis. And here's an article written in 1953 about an outbreak of infectious hepatitis in Baltimore in 1951. And that led to the people stopping to do this. No more, no more. Okay? And since the 1940s, people have used evacuated blood collection tubes because they can automatically draw a predetermined blood volume, and switching between tubes for additional samples pose a lower risk of spillage and needle stick injury, and you use it all once and throw it away, right? That's been the hope of this. So far, good. Glass evacuated tubes containing anticoagulants were commonly used from the 50s to the 90s. Anticoagulants to stop the blood from coagulating, from thickening, right? You'd think this is easy. It's not easy. They started by using the wrong form of glass, okay? They used something called soda lime glass, and it would actually leach out things like calcium ions, and it would interfere with the tests they were doing. So they had to stop that, okay? And then another thing happened, and this was more recent, at least in the United States. An organization called OSHA decided that it was unsafe to use glass in hospitals and clinics. Why? Because doctors and nurses would drop the blood-filled glass tubes, they would shatter, and then they would cut themselves on the glass and become infected. So now they have demanded, they have made it so that you must only use plastic. Okay? Plastic doesn't break when you drop it. That's, of course, good. like plastic milk bottles. The same switch has been taking place in many places. So that's what's happening. Okay? They are manufactured through an injection molding using what are called polyesters. I'll show you what those are. These are polymers, most commonly being something called polyethylene terephthalate, or PET. You've seen lots of bottles with PET as its name, or combinations like that. And now, what is it? Let's see if we can see it. This part is rigid. This is a benzene ring, and so forth. Here's a linkage. This is an ester linkage right here. This is where an acid and a base would react to form an ester. And this part is flexible, and I've tried to highlight this for you. So this is called the terephthalate group. This is the ethylene group, and that's why it's polyethylene. And this is repeated again and again. That's how you make polymers. Polymers are an amazing thing. If it weren't for polymers, most of us would lose our clothes and be a bit embarrassed. Okay? So much is done with polymers today, but these tubes as well. So here's what's good about them, if I might. Let me try to explain what their advantages are. Compared to glass, plastic minimizes exposure to biohazardous materials following breakage. It has a greater shock resistance. It tolerates higher centrifugation speeds. People spin it around, centrifuge it. Okay? Weighs less, lighter. Has excellent dimensional precision, and is more easily disposed of by incineration at a lower cost. Very hard to incinerate glass. Okay? This part works. Okay? Now, let me give you a sense of what's bad. And this is really starting to show you by looking at this leaf that you see here with water balling up on this leaf. This is hydrophobic. Okay? And plastic tubes generally have a hydrophobic surface. They hate water, and they do not efficiently activate the coagulation process. Clots formed on the plastic surface of tubes are gelatinous compared to clots formed in glass tubes. Blood does not flow smoothly. Okay, these are the type of problems you have. No one today uses bare plastic tubes. They're that bad. You have to fix this problem. They take out things from the blood and interfere with the tests. So what does the manufacturer do? Let me show you. Here's the manufacturer's fix. And what the fix is, you spritz in, you squirt in detergent. You add a surfactant coating to the inside of the blood collection tube. Okay? But these can leach out and interfere with the blood analyses. And this is why Dr. Bowen came to see me, because they're causing him a lot of trouble. He says, do something about this. And indeed, this is what I thought of doing. And I'm going to show you what I think is relatively easy chemistry. In some sense, it looks like magic, but it's something that all of you could do if you wanted to. And it shows you the power of things. Here we have a surface that hates water. How are we going to make it so it likes water? It's a common problem. And it's a problem that we all face about what causes things to dissolve other things. And generally, the expression is that like likes like, right? We want to make something similar. So to make it similar, what we really want to do, you know, water is H2O, HOH. Well, you want to put on the outside of the surface OH groups called hydroxyl groups. That's what we want to do. And I'm going to show you how we do that. And here is then a little bit of some chemistry. Here is an alcohol and some type of organic R prime and OH. It goes up to this thing. Okay, that's an ester because of this linkage. This would be a COOH, would be an acid. This is a COOR prime, double prime. That's an ester. Okay? And this alcohol plus ester makes a different alcohol. See, R primes change to R double prime. And with this, they interchange. To make this process happen, you can attempt to use a strong acid to catalyze the process. The magic word in chemistry is catalysis, to find something to speed things up, which itself doesn't really play a role in what's happening. It intimately gets involved, but it's recovered. It's recycled in the process. Look what happens. If you add, however, a strong acid to an alcohol, you're going to form an ester. This is not a good idea. This is the wrong approach. Instead, a strong base is what you want. And you want a strong base to catalyze the reaction by removing a proton from the alcohol and thus making it what we'd call more nucleophilic, so it can do better attack. And in organic chemistry, a nucleophilic addition reaction is an addition reaction where a chemical bond with an electron deficient or electrophilic double or triple bond or a pi bond reacts with the electron-rich reactant termed a nucleophile with the disappearance of the double bond and the creation of two new single bonds or sigma bonds. And now, next idea. And it's an idea that's taken me a while to first realize. I didn't get this at all in high school, at all. It just came up later. The idea that you could actually find a base better than OH. But the only way you can do that is not work in water. Water, 55 molar, stops you. If you will go to what's called non-aqueous, you can work with things called superbases. And superbases are extremely strong base that is a compound that has a high affinity of protons, for protons. The hydroxide ion is the strongest base possible when you have water, but bases exist with even much greater strength for protons. And we're going to use those. So here's our proposed fix. Our fix is to chemically convert the inner surface from hydrophobic to hydrophilic. And that's the goal I had in mind. And I'm showing you what we're doing. Here is our PET, repeated, link after link, that looks like this. That's our polyester that's made this way. We're going to add this type of alcohol. This particular alcohol is called ethylene glycol. It's the material of antifreeze. It's very cheap and common, very cheap, okay? We're going to use a base. First I tried potassium hydroxide, but later on I went to these special things which are even stronger. These are super bases. They have names. You can read them, and I'm not going to bother to say them, okay? But you get the sense of them. And we're going to use them to try to make this transesterification, you see, where we put OH groups on the outside. That's what we're doing. And that could be really neat. It turns out the chemistry is not original. It's been done before, that type of transesterification. Believe me, not original at all, okay? But the idea of making a new material, particularly a surface, appears to be original, or at least it's original to me. And so far we think it's original. So the question is, of course, after this big preamble, does it work? Well, I wouldn't stand here before you if I didn't have some idea that it worked. But let me try to convince you that it does work. And the best way to do that is to show you two test tubes made out of plastic, made out of PET. This is the PET that's unmodified. You see the water? The water just doesn't like the glass, flat. What about this one? This is the one that we've treated. I call it a chemopet instead of PET, okay? Our chemopet, look at the water. It bends up and loves the glass. That's the meniscus. And just like glass itself, it loves the plastic, you see? So I've turned the plastic to act like glass. So it looks like that. And I'm showing you before treatment and after treatment. And I'm doing it on plaques where you can actually, again, see how this water droplet spreads out and looks good. Okay? What's more about this is now very exciting to me. You can do this at basically room temperature, at least room temperature where I live. Okay, 22 degrees centigrade. And this is this particular super base with ethylene glycol. And look, 10 minutes. And you don't use up hardly the catalyst. It's a catalyst. The ethylene glycol amount is only surface. It's only a superficial process. Hardly use it at all. So it looks very easy to do. And now the next thing is to assess the performance. I didn't know fully the nature of this audience. I don't want to spend much time on this, but rather to just give you a flavor that, of course, now that we have these tubes, we can try them out. And people look at things as cortisol and triiodothyronine, the TT3, and this thyroxine, which is TT4. And we've made these tests. And here we are. We're comparing them against what is on the market. These are commercial tubes. These are our chemo pets. Okay? And here's our biases and how they're comparing with other groups. Now, it's not a big study yet. We have a study with 50 people in progress, but this is just 5. But I'm trying to show you an idea. This really works quite well. That's what it's like. Here's this one. It works well. Okay, here's the next one. It really works, so again, quite well. And so here's the tentative conclusions. Our chemo PET tubes showed lower biases than the BD. This BD stands for Becton Dickinson. They have a company that makes tubes, plastic tubes, and had a similar level of biases as these Greiner tubes. And considering the costs involved, we think we have a much cheaper way of manufacturing all this stuff. So we're hoping people will start to take this up. It's as bigger, though, than just working on plastics. But let's back off a moment. One more persuader. A lot of people lately are interested to know their testosterone levels, particularly men. Okay, and they go and they run these tests, and they would like to do them with mass spectrometry. They're a complete failure with these detergents because the detergents interfere. With these tubes, they're quite successful. It's another persuader why these tubes could be valuable to you. Okay, so are we sure about the surface modification? I mean, I've told you about it, and the chemistry sounds good, but do we really know, okay, that it's so? Now, this is difficult, but I thought I'd share it with you. And so we're getting into now the natures of chemistry. Chemistry can not only make materials and then test the materials, but we can analyze what we've made. Here we need to do a form of chemical analysis. And the particular technique we're going to use is called ATR-FTIR. And what is this? This is a total internal reflection resulting from what's called an evanescent wave. I'll explain that to you. A wave that peaks in at an interface to the material. A beam of infrared light is passed through a particular crystal in such a way that it reflects at least once off the internal surface in contact with a sample. We have to actually press it onto the crystal. And this reflection forms the evanescent wave, which extends into the sample. The penetration depths sort of on the order of the wavelength of light. Okay, and it's typically between 0.5 and 2 microns. It's falling off exponentially. And here's very much the source, how it's done. And these are now tests you can do. It is really possible to see a monolayer, a single layer. This is fantastic. And here's an IR source in the infrared, redder than your eye can see red. That's infrared. Bounces around here. You see it bouncing many times in this crystal. Here's where we put our sample. That's where we put what we've modified, and then coming out here to our detector. And indeed, I can show you this is the FTIR spectra of unmodified PET in black and the modified PET in red. And then you can actually subtract the two from each other, and you can see the OH bands this way, and you can make out that indeed we have indeed added OH to this material. We know we've done that. We don't know how much, but because it's hard to then make that into the numbers, but we have confidence of this type of chemistry. So let's do some further characterizations. And this may be yet more technical, but it's not difficult to understand. Surface modifications caused negligible weight change of the tube. That was just weighing it. So that's for all, just a surface effect. Tests revealed no leachable residues. We sent it out to other labs who proceeded to see were there any volatiles coming off. It's what we call a covalent bond. It's permanent. And we know it's permanent because we've looked a year later after we've made the tube, and it's still acting the same way with regard to water meniscus and so forth. This is what you expect. So it really has a good shelf life. So next question is, okay, fine, I told you all about PET, but is this process general? And of course, that's some of the beauty of chemistry. once you start to understand something like this, you can generalize it to try to apply it to other materials. And some of you are familiar with a material called polycarbonate. Polycarbonate is tough and stable, and it can resist a high temperature and so forth. It's non-toxic, it's stain resistant, it's 1/10 the weight of glass. Being so tough, people don't make tubes out of it because it isn't ductile in any easy way. But can we modify this? And the answer is yes, we've actually done these contact angle measurements, and indeed we're able to show that we can also modify the polycarbonate, though with more difficulty from this process. I hope this is giving you then an idea of this field. It's one example, and it shows what you're able to do with a little bit of chemistry understanding to really change the nature of materials. Yes, it's magic, but it's magic that we understand and can control and do much more with. There's going to be yet more exciting developments, I believe, presented to you today that'll impact our lives. Here's a very simple one, and I thank you to have this opportunity to present this to you.
Thank you, Dick. Apologies for believing that Bengt actually was trying to impersonate John Cleese when I said that. But no, he really slipped. So,
he was attempting to fly.
Yeah. So unfortunately, he had to go to the hospital, so he won't be here today. So to chair this session, instead, we have Magdalena Eriksson, who is also on the board of Molecular Frontiers.
Good morning, everybody. It's great to see this room full of people, even upstairs. So I think Bengt's introduction of Dick was a little bit interrupted, but you can see that Dick is an enormously enthusiastic person who works in different areas of chemistry, and this was one exciting example of that. So if you have questions, feel free to raise your hand, and the microphones will come from the side or the aisles of the room. Who's first?
Any thoughts about this?
Do you ever wonder what happens to your blood?
Thank you. So you said that the important thing is that the blood doesn't interact with the material. So what does it matter? Does the material like water or not?
So
does it stick to it or not? What is it?
So you see, it really does like water, and it's not causing the things which don't like water, things that are called like fibrinogen and other things, to stick to the tube. It's making it so it can easily be smooth and it doesn't stick any further. Okay. As you know, most biological fluids contain water, right? And we don't want to take things out. No, most of us are all wet. Almost all wet, right? and that's what you want, so it doesn't interfere with the system. That's its nature. We didn't know ahead of time how well this would work. And I'm just giving you a sense of something about research, if I might. Almost all the time, everything in our lab doesn't work, fails, go through stages of failure. And this is very important because it's not like what you get in high school. High school, they design labs that always work, are supposed to work. Even those don't work so well, but they're supposed to work. In real research, things don't work often. You have to be patient and persistent, and you have to let failure guide you, honestly, to make things work. It's an important part of, if you want to be a researcher. But it's rewarding, so exciting, those moments where something starts to happen. So for some of us, can't stop doing it. It's a passion.
Any arms raised? No? You know, I don't want to challenge you, but in Singapore, you can't even keep up with all the arms that people raise. So please. So let me ask you, Dick, what happens when you get an answer to a question? How many more questions do you normally start asking?
So now, of course, we're trying to. There are further questions we don't know the answers to. How many various sites that we really modify? Okay, I don't know fully the answer to that. Need to try to find that out. Maybe there's some way of titrating it or something to find out. We've done other techniques. There's some very fantastic forms of microscopy that today one can have. So far, we've used like atomic force field, but we haven't learned anything from it. We're trying, but it's really changed. One of the amazing things that's happened today, from the time when I was your age till now, is that people can look at individual molecules. Okay? Really believe, we prided ourselves that we believed in them, but no one had seen one. That's all changed. You can see them in a number of different ways. They're so. Okay?
Mm-hmm. There will be a discussion.
Question over
there.
here.
Great, yeah.
How can you stop blood from coagulating?
They actually add materials that are anticoagulants. Now, I don't know enough of the chemistry behind that to know how that slows that down. But I know there are such materials. Heparin, I think, is such a material. But I don't know fully how it works. Maybe someone else does. But there are such materials that people use regularly. And you know, there's so many tests we now run with blood to try to figure out what's with us. It's important. Dipstick, okay? Like we do a dipstick into an engine and look at the oil looks dirty or not, how it is. Well, we look at blood and try to learn from that and other bodily secretions and to get a quick idea of what's happening with us. Yes?
You ask, is this approach universal? And you don't answer your own question. To continue, my question is, have you considered changing not only the chemistry of the material, but also the morphology of the surface of the material? That will influence very strongly the hydrophobic, hydrophilic properties of it.
I have not done much, but I know that in general a rough surface is worse than a smooth surface. I hope you agree with me. Maybe you're not. I don't know.
Worse or good in which sense?
I think a rough surface has more surface area and can generally pick things up more. So these tend to be smooth surfaces that are being modified. But I don't know if that's what you meant by morphology. Maybe you meant something else. And it may not be the only way, but plastic's really cheap and it's easy to work with, and this looks like a simple fix to a problem. And so I hope people might take this up. We'll see. And way back.
I wonder, this technique, is this possible to use like in other things in daily life? Have you thought about that? Like, hating and love water. If you can use it like in other things except this blood thing.
If I understand the question.
Can you please ask the question again?
Yes,
Sorry.
this technique that you have used to discover what you have discovered, is it possible to use the technique to other things?
Other things.
In your daily life?
Okay, so far I think it's general to what we call polyesters, to things that have nucleophilic backbones to do this type of chemistry. But the idea of surface modifications is a big field. And this is just one example of what I think many people are doing or can do. And
yeah, well, I think we move on and you
Thank you.
come back for the panel discussion in the afternoon. Thank you very much, Dick. Can we give him a round of applause?